In this video, we're going to take a look at drag. Drag is air resistance, and there's a video here of a wingsuit, which is a big suit that you can wear when you jump out of an airplane or off of a cliff and that kind of thing. I'm not going to watch the whole thing here, but it's kind of a fun thing to see that shows how changing the air resistance of your body can really affect your free fall. And you can, again, watch this on your own. You can follow the link. But the force of drag, usually FD or capital D occasionally, is air resistance. And it's very similar to kinetic friction in that it's only really present when things are moving. However, it depends on velocity, which is different from the sliding or kinetic friction that we've already looked at. There's a couple different ways to consider it. If you have a fluid moving past it, you have an object moving. Either way to think about it, it's a relative velocity, and it tries to reduce the velocity of an object. What does it depend on? Well, it depends on the velocity, the area of the object, the fluid density, the shape, the roughness, and various flow characteristics. All that to say, it's a fairly complicated thing. And the equations that we use for it, just like other friction, are empirical. They're based on experiments. So the formulas we use in this class involve drag is equal to negative kV, where k is some constant, or sometimes drag is equal to negative kv squared, where v is the velocity, and the negative sign indicates that it's opposing motion, or it's a retarding force. In your textbook, you'll see this format. Really, that 1/2 C rho A are all just put into the constant, the K in the AP formula. But so we want to think about what happens here. Well, if the velocity is to be used, or the velocity squared, it depends on whether it's kind of laminar flow, lower velocity, or turbulent flow at higher velocity. So sometimes one is a better model than the other. Density is how thick the fluid is, not the object, the fluid itself. So if you're going through, molasses, it's different than going through the air, just like going through the water is different than going through the air. The cross-sectional area matters in the direction of the flow. So how much of the air is blocked, but also the drag coefficient. And this depends on the shape and the surface roughness. And again, this is empirically or experimentally figured out. All of this is inside the K. Everything that's a variable, it's that 1/2 C rho A piece. So how do we deal with this? Well, drag varies with the velocity. So when you first jump out of an airplane or a helicopter, zero velocity, no drag force. As you fall, the drag force starts to get bigger and bigger. And eventually you reach a point where the drag force is equal to the force of gravity and you stop accelerating. This point ends up being very important velocity. That velocity that you reach, that is what we call the terminal velocity. It's the fastest you can fall, or any object can fall. The air resistance force is equal to the force of gravity. Terminal velocity is a first law situation. Net force is equal to 0. Drag force and force of gravity are equal to each other. For laminar flow, you can kind of set up this relationship that K times the velocity terminal is equal to mg, which means that the terminal velocity can be found if we know this K by dividing the force by that constant. As V increases from 0 to V terminal, we're using Newton's second law, right? If the drag force is smaller, we have an unbalanced set of forces, and we have an acceleration down that is less than the acceleration due to gravity. Right, so we could find that acceleration. When we're considering this, we can actually solve a differential equation, and we'll deal with this later once everyone's gotten a chance to solve and look at the solutions to various integrals and derivatives. But suffice it to say that we have to solve this to actually come up with a numerical answer. For us right now, the really big idea is just that terminal velocity occurs when the force of drag and the force of gravity are equal, and we're going to look at that first law situation. Or we'll look at individual snapshots where we know how much force is being applied.